Good afternoon. The Atoms Group is pleased to have with us Professor João Coutinho. He is full professor at the Chemistry Department of University of Aveiro, Portugal, where he is Vice Director of CISECO, Aveiro Institute of Materials. He leads a multidisciplinary research team that focuses on development of green solvents and novel separation process for biorefinery and circular economy. Currently, he strives to apply bio-based solvents, deep euthetic solvents, and ionic liquids to this process and attempts to better understand their physical-chemical behavior. He's authored over 600 refereed papers, which to date have been cited more than 25,000 times, and also authored 12 patents. His research interests range from the exploitation and fossil fuel transport to the production and formulation of biofuels, the characterization of non-conventional solvents for the development of new products and chemical process, the characterization of biodegradable polymers, and biotechnology, hence the octopus photo. On the last domain, he was one of the responsible people for the creation of the bachelor and master's degree in biotechnology at the University of Aveiro. He's currently addressing most of his research time to characterization and development of new applications of ionic liquids. So welcome, Professor Coutinho. Thank you, and you now have the word.
Thank you, Yamara. And thanks to you all. Thanks to Atoms for inviting me, but most of all, congratulations to Atoms for this wonderful idea of creating this series of seminars that not only me, but my team, and I noticed that many people in Brazil and around the world have been profiting for. And it's my big pleasure again to be speaking to you all and to be in the list of these seminars among so many important researchers on the area. These, I don't know how many of you have seen my, not lecture, but my course that I gave at CB. Some of the material that I will be presenting today was presented also there, but there's a big part of it that is new results, very new recent results that were the result of a work in collaboration with one of my youngest students, Denise Branches, and that's why he's cited here as co-author, because he has been really a co-author and not just someone that is doing the work that I'm asking for. And this is the team that I've been working with on these deep euthetic solvents. Some of them are no longer with me, but this is the person that I would like to sign up that is the co-author of this talk today on both the euthetic systems and the hydrotropes. And without further delays, I will go directly into the topic of the talk of today, because it's probably too large and I don't want to stay here with you the entire afternoon, and I'm sure that you have other things to do as well. What do I work on? I already mentioned, but my main field of work nowadays, I tend to think of it as sustainability. And in this sustainability, and I've been heading the sustainability research line of CISECO until I became the vice director. And for me, what I do is to develop eco-solvents. There are many eco-solvents. Probably the best one is water. The problem with water, you know, is that water, although a wonderful solvent, it doesn't dissolve everything. And in particular, it never dissolves what you want water to dissolve. And that's why I work in trying to modify the water properties using different things that I add to the water, like additives. And two of them I will talk about today. One is euthetic solvents and the other is hydrotropes. And you will understand that I talk about euthetic solvents because I don't like very much the concept of deep euthetic solvents, as I will explain briefly, really briefly. And why do I want to address this and start by the very basics? It's because euthetic is a concept that is with us for almost 150 years. It was created in 1884, and it's well understood today. We have equations to describe it. Every thermodynamics course teaches the solid liquid equilibrium equation that relates the temperatures of fusion of the mixture with the composition of this mixture and the activity coefficients. But suddenly, in the last few years, people seem to rediscover the euthetic point and euthetic systems as if it was something completely new. They will tell you that it's different because now it's deep, but they don't explain what is deep. And the melting point depression that seems to impress many people is just a colligative property. And colligative properties are properties that depend on the concentration, essentially on the concentration. It's just a matter of statistics, meaning that since you have less molecules of one type, it's more difficult for them to meet each other, so the melting point decreases. Same thing for the boiling point. It's more difficult when instead of 100% of molecules of one type, you have molecules of different types. That two molecules of the same type meet together and 3 or 4 to create crystallization nuclei or bubble nuclei, so that you change the phase. And that's the reason why we have boiling point elevations and freezing point depressions. It has nothing to do with interactions or anything else. Even without favorable or unfavorable interactions, you will have melting point depression. And that's why when you see in prestigious journals like PCCP titles like, "Is the ideal thermodynamic creator the key to formation of deep euthetic solvents?" This makes my blood boil, because this means that people do not understand the basics of thermodynamics, let alone of physical chemistry. And they do not understand the basics of deep euthetic solvents, because when Andrew Abbott created this concept, he created and he established it very clearly. First, he clearly, and this is from a chemical review that he wrote a few years ago, he clearly stated that deep euthetic solvents are euthetic mixtures. And many people are treating them as if they were pseudo-compounds. And they are euthetic mixtures of fluids and brownstates, acids and bases. It's in the acid-base interaction and not just an hydrogen-bonding interaction that he was discussing this. And they were obtained by complexation. And in the cases that he was studying, it was mostly salts. And I will show you that this is not only for salts during my presentation. The problem with this definition of deep euthetic solvents is this figure and this concept, because Andrew Abbott assumed that this delta T was what he would call the difference between the theoretical ideal mixture and the real mixture. But as I told you before, an ideal mixture, even an ideal mixture from thermodynamic point of view, would have a melting point depression. So this delta T and this graph to describe what is a deep euthetic solvent is meaningless. Deep euthetics are based on a concept that is solid liquid equilibrium. And it's amazing that so few people study solid liquid equilibrium to understand better these systems, and instead they just go directly for the applications or trying to understand the liquid phase without going into what I think that is the most important thing. It's the phase diagrams. The phase diagrams are the key to understand the deep euthetic systems. And that's what we have been doing in my group. Since a few years ago, we start measuring phase diagrams, sometimes very quickly, very simply, just looking into the liquid line instead of looking to all the details that may be below the liquid line. And in many of these cases, these systems can be far more complex below the liquid line than many people admit. But using them to understand better the nature of the euthetic solvents. And first thing that you have to understand is when you have an euthetic, that the euthetic is dominated by two things. One of them is and forget about this term that is not very relevant, is the enthalpy of fusion. this liquidus line will change with the enthalpy. If you have a high enthalpy of fusion of pure compounds, this line will be moving up. This means that you need higher temperatures to melt a compound. But if it has a low melting enthalpy, this line will be moving down. You will achieve exactly the same effect through the activity coefficients. That is the non-ideality, that is the interactions that everybody mentions. Meaning that if you have a non-ideal behavior that is with positive deviations, meaning that the compounds interact poorly between themselves, oops, you have also the line moving up. While if you have favorable interactions, the line will be moving down. So to achieve a drop on this line and to have a larger liquids region, you can achieve it in two ways. One is with a lower enthalpy of melting, and the other is with favorable interactions. To understand how the basic systems with the choline chloride, that seems to be the thing that people favor most to prepare deep euthetic systems, we need to have the melting properties to study these things. And the problem with choline chloride is that it decomposes upon melting. So you really cannot measure its melting temperature or its melting enthalpy. So the first thing that we did was to develop a technique to indirectly access the enthalpy and the temperature of melting of this compound so that we could then study the interactions of this compound with anything else. And we did this is reporting this article. I won't go into details, but basically the idea was to prepare mixtures that would have a near ideal behavior, make sure that the behavior was approximately ideal, and then extrapolate this line and to obtain a melting temperature and a melting enthalpy. Many people would agree with melting temperature. It's just the extrapolation of the experimental data, so it's not much doubt about that, but many people would claim also that this value is too low. And they claim that, and they are right, this value is very low for an enthalpy of fusion. The problem is that choline chloride, like many people admit or know, has a solid-solid transition close to 80 degrees. And this has been known since 1957, so more than 60 years ago. And this phase, this high temperature solid phase, is disordered. The same author, Colin, in 61, he reports finally the structure of this high temperature solid phase, and again he showed that it's a disordered phase. What happens is that at around 80 degrees C, as you see here, it goes from the orthorhombic phase of low temperature to a cubic, very disordered phase. So it has a pre-melting and with a very high enthalpy of solid-solid transition, and that's why at very high temperatures, or the temperatures above this 80 degrees, it has a very low enthalpy of melting. And that's why actually choline chloride has a very steep drop in the melting enthalpies. Most people are looking for the reasons in the wrong way. They are looking for the interactions when actually the question is the enthalpy of melting. Because when we use these properties, then to calculate phase diagrams is absolutely surprising. And this is the most common example of a deep euthetic solvent, the choline chloride urea. And these experimental dots are the experimental data points, and the lines are the calculations using the ideal solubility behavior. So activity coefficients equal to 1 using the equations that I showed you before. And as you can see, the choline side, this is the choline side of the phase diagram. It has an essentially ideal behavior. Then it deviates towards positive deviations, not negative deviations, below the solid-solid transition of 80 degrees. Where do we have deviations to the ideality and negative deviations? On the urea side. So it's the urea that has negative deviations, not the choline chloride. And I won't go into details of this. We have other articles where we detail the interactions. What is interesting, and this is an analysis. We had shown this before, but this is a very interesting analysis in a very recent article that we have in a special issue about the Euthetic solvents in Journal of Physics and B that I suggest that you give a look, not just to this article, but also to the special issue that is being prepared. Is that when you mix choline chloride with model compounds, and we did this with a number of model compounds, but here I will show you the fatty acids and fatty alcohols as examples of acids and alcohols. What you see is that choline chloride, and that's the line here, the line is the ideal line, and the dots are the experimental data points. It has positive deviations or ideal behavior. The same thing for the acids. And when you mixed it with alcohols, it's the same thing. The choline chloride has essentially an ideal behavior, and the alcohols have a positive deviation. So in most cases that we have studied so far, we have found that choline chloride always has either an ideal behavior or even positive deviations to the ideality. So it's nothing special about choline chloride except for its very low enthalpy of melting. And the question then that we had was two sides. Is choline chloride mixtures or are choline chloride mixtures always ideals? And is it possible to create really deep euthetic solvents in the sense that you have systems that strongly deviate from ideality? Well, I've been working with solid liquid equilibrium since always. It was my PhD thesis, so I knew that it was possible. But what we have been doing in this last couple of years is essentially to try to develop the heuristics that will tell you which kind of molecules you should use and understand better the type of molecules that can really produce strong negative deviations to the ideality. So the first thing was to probe choline chloride. It's always ideal. We start mixing choline chloride with a series of other chloride salts. And to our surprise, although choline chloride had either an ideal behavior or near ideal behavior, on the other side you have always positive deviations. You see, for these four systems that I showed you here, this is the side of choline chloride, it has always positive deviations to the ideality. So not only choline chloride is not very good at decreasing due to interactions, when mixed with other salts that are chlorides, it has actually positive deviations and not negative deviations. And we start thinking about the type of interactions that choline chloride had with the chloride anion. And this is a very interesting work where it's by Patricia Hunt. It has already a few years, but she studied here by having these calculations, all types of interactions that you can find between the cation and the anion. And it's very interesting because although this is the most stable one, it's like a claw of the cation holding the anion. She also found this one that although its energy is far higher, it's the most probable thing when you have quaternary ammonia. So we thought that if we would remove this, the hydroxyl part, we could probably improve the interactions and achieve what was our goal, negative deviations to the ideality. So what we did was, let's replace these mixtures that we did before with choline chloride by the same molecule, but now without the OH group. And what we obtained was that the quaternary ammonium now can produce either ideal. Remember that previously with choline chloride we had strong non-ideal positive deviations. Now it's either ideal or, depending on the second compound, they can be non-ideal and even strongly, very, very strongly non-ideal. And we studied this in detail with many compounds, but the most interesting series is with quaternary ammonium itself. It's interesting because when you mix the quaternary ammonium, the tetramethyl ammonium, with the tetraethyl, the tetrapropyl, and the tetrabutyl, you have very strong deviations. And this is very unexpected because these molecules are extremely similar to each other. You wouldn't expect the two ions that just change a bit in size have deviations with activity coefficients below 0.2. So something must be happening here. So we try to understand that, and well, there are different ways of trying to get to this understanding, but what we did here in this particular case was to use molecular dynamic simulations. And in these molecular dynamic simulations, what we looked was to the distribution of the chloride around the cation. What you have here in dots, this dotted line, is the distribution of the chloride around the tetramethylammonium when it's pure. Then if you mix the tetramethylammonium equimolarly with an tetraethylammonium, then you see that there is an increase on the chloride around the cation. Now, if you add tetrapropyl, you have a further increase, and if you add tetrabutyl, you have even more of an increase. What does this show you? That the tetramethylammonium chloride is able to withdraw the chlorides from the other cations. And that's why we have such strong deviations as you have seen here. Because in this case, for instance, what you have is almost like if you had dichloride of tetramethylammonium mixed with a cation that is the tetrabutylammonium, because so many of its chloride ions are around the other cation. What this shows you is that these ammonium are very prone to release its chloride. They are much less attached to this chloride than they were in the case of the collinium. The collinium is very much attached to the chloride, but the ammonium are very free concerning the chloride. And this brought us to this that I was showing in the previous slides, the new type 1 DAS, because previous type 1 were only chlorides of metals. And for the first time, we showed that we could have chlorides of organics and produce very deep deviations, negative deviation to the ideality. So a strong drop in the melting points. And that's what I'm showing here. When you mix the tetramethylammonium chloride now with fatty acids, you no longer have the ideal line that you had with collinium. You have strong deviations. Truth, the acid still behaves ideally or near ideally, but now the cation has very strong deviations to the cation. The salt has strong deviations to the ideality. And same thing with fatty alcohols that I showed you before also. Strong deviations to the ideality. So we really could, by understanding the interaction between the cation and the anion, release more freely the chloride and make strong interactions with the other compound, allowing to have very negative deviations to the ideality. And I was very surprised when, well, we also had the series of lectures that are ongoing here in the department. And a few days ago, we had invited Professor K. Sunmacher from and he was showing a process of the extraction of vitamin E using DAS, where he was using this concept, although not really understanding why he had these strong deviations. But he showed that the quaternary ammonium are very good at making DAS with tocopherol and then extracting the tocopherol. So the concept is, yes, you can do it, but you have to think about it. And we kept thinking about how to change the choline molecule so that we could have more of these deviations to the ideality. And that's where we came to the betaine. Betaine is a molecule that I don't know if many of you are familiar with, and it's a real natural molecule, unlike choline. Choline, people say that it's a natural compound, but actually choline is produced in large scale by petrochemical approaches in petrochemical industry. It's not a natural molecule. Betaine is obtained, is industrially produced as a byproduct of the sugar industry. It's present in large quantity in sugar beets, and so when you produce sugar, sugar from beets, you also produce large quantities of betaine. And betaine has many applications, in particular in surfactants and so on. We start looking into the betaine because we had been looking into the betaine for other things, in particular for producing ionic liquids or ionic deuteriums out of it. Because betaine is very interesting. It has all the things that quaternary ammonium has, namely a very shielded positive charge, but it has a negative charge, a carboxylate region that is a very good acceptor. And that's what we looked for on when we are trying to do these things. Instead of the chloride, now we have this carboxylate. And the big advantage is that although the quaternary ammonium are interesting from a conceptual point of view, from an application point of view, you would probably not like to use them very much. But betaine has all the advantages that you can think about of a molecule. It's cheap, it's producing large scale, it's natural, it's renewable, and it works as good as the quaternary ammonium that I showed you before. In the red lines, you see the quaternary ammonium. In the green lines, you see the betaine, and that's in both cases, betaine is slightly less good than the quaternary ammonium. But from an application point of view, it gives very, very large deviations, both with the acids and the alcohols. And as you can see here, with a series of new compounds, we just had this week, this work accepted in Chem2Chem. With phenolic compounds, it has very good deviations to the ideality. Look here, you have here 150, almost 200 degrees of drop in the melting point of the thymol, and even with very, very weak hydrogen bound donors, you still have negative deviations to the ideality, as you can see here with camphor and coumarin. And look at the charges of camphor and coumarin. You wouldn't even think of them as a donor because, well, you would more easily think of them as an acceptor. But since betaine is a stronger acceptor than any of them, you still can have negative deviations and really produce interesting euthetic systems with this compound. And using some descriptors from Cosmo, we could even come up with a correlation for their melting points. So it's predictive. And when you compare colinium chloride and their binary systems for these molecules that I've just showed you, they are either ideal or near ideal. And here with betaine, you really have a molecule that can produce very strong non-ideal deviations to the ideality. So strongly recommend that in your works you try betaine instead of colinium chloride, except if you really need to have chloride in your system. And that's a question that you should always ask yourself. Do I need chloride in my system? Because in most cases, chloride is not doing anything or not doing anything good in your systems. And I just show you some results with terpenes, and people have been suggesting terpenes for producing natural deep euthetic solvents. Well, we had been studying terpenes with the group in Campinas when Bernardo was doing this work. Around 15, 16, we were there trying to measure phase diagrams of mixtures of terpenes with themselves and with acids and alcohols. And as you can see here in these phase diagrams, although they produce very interesting phase diagrams, they are essentially ideal mixtures, not deep in any sense of the word. Even the mixtures of terpenes with themselves are in general ideal mixtures. So they don't deserve to be called deep in any sense of the word. Just an ordinary solid liquid equilibrium with a mixture that has an euthetic point. But, and this is the very but, in big but, is that the mixtures with T-mol, they had a surprise for us, because in these cases, T-mol had a very strong negative deviations to the ideality. And again, we had to understand why. Because when you mix a molecule like menthol with a molecule like T-mol, they are so similar that you couldn't expect, just like that, a strong negative deviation. And when I'm talking about strong, again, I'm talking about around 100 degrees between the ideal line and the actual melting point, or glass transition, because in this point here, it's even very difficult to make them crystallize. And why is that? And that's what brought us into this ChemCom that we published last year, is the understanding why we had two molecules that were very similar but had very strong deviations to the ideality. Is that the resonance of this phenol group creates a very strong acidity. So T-mol is a very strong hydrogen bond donor. Menthol is just a regular alcohol, but T-mol is a very strong hydrogen bond donor. And being a very strong hydrogen bond donor is a very poor hydrogen bond acceptor. So T-mol, menthol hydrogen bonds, they are stronger than menthol that are just regular, or T-mol that are weak. And that's how we get these very strong deviations. So by having something, and this brings us back to the original definition by Aboult. Think about acid-base interactions. Don't think just about hydrogen bonds. Mixtures of two compounds that hydrogen bound with each other does not guarantee negative deviations. They may even lead to positive deviations. But if you think about acid-base, acid donor, or proton acceptors, you really have something else. And the other thing that I would like to challenge you to think is to stop thinking about these 1-to-1, 2-to-1, 1-to-2, or these stoichiometric relationships that are completely meaningless when you really understand solid-liquid equilibrium. The euthetic point has nothing to do, except in very strong deviations to the ideality, as is this case. In general, they have nothing to do with these stoichiometric relationships. Actually, if you just want a liquid to work with, you can work with mixtures, in this case, at room temperature between 0.2 and 0.75. And this allows you to do much more work than just thinking about one thing. And this is important because look at this. This is the phase diagram that I showed you before, solid-liquid equilibrium. And this is the vapor liquid that we decide to measure to understand more about these systems. And when we look into the non-ideality of this phase, it's very interesting, but it's expectable for a thermodynamicist. That is, the solid liquid at low temperatures has very big deviations to the ideality. But as you increase the temperature, these deviations, they start to disappear. I have here this for a range of temperatures, or here the infinite dilution as function of the temperature. And as you see, as you increase the temperature, the strong negative deviations to the ideality, they tend to disappear. And that's why here the vapor liquid equilibrium is not exactly ideal, but it's very close to ideal. And this is at 500 millibar. If it was at atmospheric pressure, the temperature would be large enough to make it ideal. So the non-ideality plays a limited role on all these. Probably it's good to create this deep thing, but then it doesn't play a significant role in most systems at the temperatures that you want them to operate, in particular if you want to use this at the temperatures above the ambient. But it allows you other things, meaning when you think that you are working with mixtures, and mixtures of two compounds that have different natures, for instance, in the case of menthol and thymol, one that is a very strong hydrogen bond donor and the other, and etc. So one with a high acidity and the other with a low acidity, one with a high basicity and the other with a low basicity, one being aromatic with a high polarizability and the other with a low polarizability. What you get is a mixture where you can range a wide or cover a wide range of A, alpha, beta, or pi. And when you use this, and instead of thinking just one-to-one, you really use the entire composition range, you see that the maximum of your extraction, the maximum of your selectivity, it has nothing to do with one-to-one. It can appear depending on the interactions of each of these compounds of the mixture with the compounds that you are working with, your target compounds. It can appear anywhere depending on these properties. So this is the big challenge when you are working with deep euthetic solvents. Forget about the stoichiometric proportions. Think that you are working with mixtures. Optimize your mixture for your special purpose. I don't care too much about the hydrogen bond that is going on. And with this system, when we report it, and that's one of the things that made us into ChemCom, was to show that this was a new type that had never been described before, because all the previous types were with ionic compounds. And now we had mixtures of two molecular compounds with very strong deviations to the ideality. And this is my message. These are mixtures, but not all mixtures are these. Now, when we were doing this, we realized that it had been published in 1902, a book where people say that thymol liquefies when triturated with about equal quantities of camphor, menthol, or chloral. So you see, you can be copied by someone that was working 1 century before you. And now that's the question that many people ask me, but João, what is better, ionic liquids or euthetic solvents? Well, the problem is that when people ask this, nowadays when you read any article on this, you have always this sentence: these are cheaper, easier to prepare, less toxic, more readily biodegradable, and thus greener and more sustainable alternatives to ionic liquids. People tend to compare imidazolium cations, quaternarium ammonium, phosphonium with choline chloride mixed with other compounds. And if it's true that it's very simple, cheap, and they are not very toxic, if you mix a choline chloride with an acid to obtain a DAS, that is a mixture. The truth is that it's also very simple if I pick choline instead of chloride, hydrogen carbonate, or hydroxide, mix it with an acid, oops, I just wrote this in Portuguese, to make the colinium ionic liquid. It's equally cheap, it's equally easier to prepare. And my message is, if you really want to compare ionic liquids and DAS, you shouldn't compare choline chloride with imidazole. You have to compare choline chloride-based ionic liquids with colinium-based ionic liquids. If you want to compare with imidazolium, you can use imidazole chloride to prepare euthetic systems, and then you can compare and be a fair comparison. So what about their toxicity? Are ionic liquids more toxic than euthetic systems? Not if you use the right comparison. That is, a mixture of colinium chloride with acetic acid that you compare with the colinium acetate, or mixture with lactic acid with colinium lactate. And these bars here are higher than all the bars. These high bars are for ionic liquids. These low bars here are for the euthetic systems. Low means more toxic. The same ionic liquid is less toxic than the corresponding euthetic system for a very simple reason. The acidity, the pH of these things is very low, and microorganisms or other types of organisms. They do not like this very low pH, so they tend to be more toxic. But most people are not interested in the toxicity or biodegradability or these issues. What they care is to know about the performance. And again, we decide to make the right comparison between what is the best solvent. Euthetic solvents, choline chloride with malonic acid, choline chloride with glycolic acid, or the ionic liquids, choline malonate, choline glycolate. And we use 5 model molecules. The model molecules you will see are the same that you will see in many of my works, because I'm concerned with biomass things. So it's gallic acid, benzoic acid, so 2 phenolic acids, spiritin, vanillin, and tryptophan. And I choose these molecules not only because of their bio-related compounds, but because these 2 are acids, these 2 are molecules that I would call neutral molecules, and this is an amino acid. You know that it has a amino group, so it can behave as a base, but it also can behave as an acid depending on the pH range. And as you will see, this is very important when you do these things. Let's look at the results that Jordana did for us in the last couple of months. Jordana went to the lab and measured the solubility of the benzoic acids in these 4 compounds. And the circles are the ionic liquids, while the diamonds are the euthetic solvents. And these are the pH. As you would expect, the pH for the euthetic systems is very low and increases when you add an acid, while the pH of the ionic liquid was about 7, and then it changes a bit, but not very dramatically. And as you would expect, an acid is more soluble at higher pH than at very low pH. It doesn't work here very well like dissolves like. The same thing, no, before that, this is, oops, the line that you can calculate for the solubility of the compound as function of the pH. So it's expectable that things dissolve better at higher pH. But note that it doesn't follow exactly the pH line at very low pH. Even when you decrease the pH, if you increase the concentration of your euthetic, it really increases solubility significantly above the baseline. Then the gallic acid is exactly the same thing. The ionic liquids, they present a higher solubility than the euthetics. And when you go to the neutral, let's call neutral molecules like vanillin and the spiritin, well, things start to change. In particular, at low concentrations, you have already the euthetics that can be somewhat better. At higher concentrations, the ionic liquid are better. Similar thing for the spiritin, where one of the ionic liquids that is choline malonate is clearly better than the others, but the other 3 are very much similar. And when you go to tryptophan, now that you have a molecule that can behave as a basis, dissolve a basis in an acid, and you really get a better result than if you dissolve it with another basis. And the results, this is the tryptophan solubility as function of the pH, and this is the effect of the different compounds. You see, the message here is one of the things that driven the solubility of compounds. The first thing is the pH. And if you are using solutes that have different solubilities at different pHs, instead of thinking about DES or ionic liquids, think about what pH range do I want to improve the solubility of my compound. And that's the key. What is better? Is the ionic liquid or the euthetic solvent? It's a senseless question. The right question is, what is the pH that you want to achieve to enhance the solubility of your compound? And then if you want to an acid pH, well, an euthetic system is probably better. If it's a more neutral or alkaline pH, then certainly you can achieve that better with an ionic liquid. This said, this is the case for these 4 compounds that I compared here. And as this image clearly shows, there are other secondary effects that must be taken into account. And that's where I'm adding to in this last part of my presentation that is already very long. Why did I start working with the euthetic solvents that I always disliked a bit? Because of this CEPI. CEPI, that is the Confederation of the Pulp and Paper Industry here in Europe, decided that the euthetic solvents would be the solvents of the future for pulping. And they create a big European project that we were involved on to create a pilot plant of pulping with DES. The concept would be very simple. You use the wood with DES, you do pulping, then you precipitate the lignin and you recycle your DES. The concept is very simple, but it's very difficult to achieve, and it was even more difficult when they start this because they had no idea how the solubility on euthetic systems would occur. And what I want to show you, well, this is the lignin that was the molecule that we had. It's actually not lignin, it's just a model to show you that there are a number of different monomers, that's the monomers that we decide to study the solubility in solutions of we study different DES, and I always work, as I told you, with aqueous solution. And what is interesting is that this goes through a maximum that is typical of an hydrotropic dissolution. Later on, I understood that hydrotropic dissolution doesn't have to go through a maximum, but if there is a strong maximum, this is a very, very good indication that there is an hydrotropic dissolution. This allows us to select the best DES to dissolve the model, then showing that the same DES could dissolve technical lignins, and then producing pulps that had similar characteristics. This is the pulp that the cellulose fibers compared with the kraft pulp. No, these are the cellulose fibers that we have compared with kraft pulp. And they are very similar from all the characterizations that we did. And that's why I was interested and I was coming to this concept of hydrotropy. Hydrotropy is a concept that is very important and very few people realize, because very few people work with. If you are working with formulation technology, you will be very familiar with this. If you are working with drug formulation, you will be very familiar with this. But if you are just working with solvation and thermodynamics and so on, probably you never heard about hydrotropy. But hydrotrope is just a compound that solubilizes hydrophobic compounds in aqueous solutions when it's added to the solution. Typically, it's something that is an amphiphyll, but with a very short chain so that it doesn't self-aggregate alone. So we need something else to self-aggregate. There were a number of hypotheses for the mechanism of hydrotropy in literature, but recently, a few years ago, Professor Shimizu from York proposed a new model, a new concept from which he derived from thermodynamic statistics, a new model that is this equation that I will be using here to treat the hydrotrope solubility. It has essentially three parameters. This parameter here, that's maximum solubility, the M, that is the number of hydrotropes per solute, and the P, that I won't go into details. As I told you, you recognize the hydrotropy either by this strong maximum or the sigmoidal. That's the most important thing. Sigmoidal-like profile in your solubility is a strong indication that you have hydrotropy at place. And to study the hydrotropy, we have plenty of examples with ionic liquids. We published an article on that with ionic liquids. It also works with DES, as I just showed you with the example of the lignin. But to understand the basics, to understand the fundamentals, we need simpler molecules. And we have been working with simpler molecules, simpler hydrotropes, like these glycerol ethers, where we could easily change the chain, then increasing the non-polar part, keeping the polar part. That's very important for hydrotropes. And again, to model compounds that you would expect in our work, scalic acid, syringic acid, not only because we work with them, but also because you see, you can change their polarity, and this is also important. The first thing that we did, beside making measurements, was to understand the mechanism. And to understand the mechanism, we used NMR. when you do the NMR, the chemical shifts are related to the chemical environment that the molecule has. And what we observe is that there is a chemical shift deviation in this part of the molecule that is very much related to this part of the molecule in presence of the solid becoming more apolar. So the environment that this part of the molecule feels is more apolar than when the solid is not there. This means that the molecules start to aggregate with themselves and with the solid. And this gave us the first evidence, experimental evidence for the model that Professor Shimizu had proposed. It's very interesting because the lowest deviations are for this carbon here, that is in more polar part. And secondly, it's for this last one, showing that this last bit of the molecule is already in contact also with water and not just with apolar. So these are not micelles where you would think that all this part is in the non-polar moiety of the micelle. So this is the concept, the idea of how these things work. Hydrotropes are there in solution. When you add a solute, they aggregate around the solute, increasing the solubility of this solute. And increasing can mean 1,000 times. We try to go far from this and try to quantify these things, and using this measure of the apolarity. This is a map that you get from this charge surface that we calculate with Cosmo. And when we correlate these apolar factors with sectional constant, you really have wonderful correlations showing how these things are related, meaning that the more non-polar is the molecule, the more you can increase the solubility. So the non-polar part is really the key to achieve this enhanced solubility. And the other thing that we could get from the M from this equation, that, as I told you, is more or less the average number of hydrotropes around the solute, is that there is a maximum. Maximum like you have, for instance, in the surfactants in your HLP, or when you are working with solubility parameters, you also have this maximum, meaning that you really have to design your hydrotrope to match the apolar factor of your molecule so that you can maximize the interaction between the two and maximize the solubility. So this gave us proof of the mechanism, but also indications about how to design these compounds. Another very interesting solvent, green solvent, and this is so much more greener, so much more interesting than ionic liquids or deep euthetic solvents, is styrene. Styrene was first reported in literature in 2014, and last year they already opened a 50-ton plant. And this year they will be opening a 1,000-ton plant. So these are the things that we should be working with when we talk about green things. And they were recently shown to be hydrotropes, and we also use this molecule. This molecule is a fairly complex molecule because it can form a ketone or a diol, and diol can interact with water and with some acidity. But let's think, this line here is for the ketone and this line here is for the diol. We will be working mostly around this region here, so it's clear that the ketone is the key for this thing. And we and the literature study a number of solutes, and as I told you, the sigmoidal curve shows that there are hydrotropy here, and the colors show that this is very complex because there is a region where the diol is dominant, a region where the ketone is dominant, and then there is the other side of the maximum that I won't go into much details today. The point is, when you treat these curves with this model, and we will be looking into the region that is reaching ketone, where you achieve the maximum of solubilities, you get wonderful values of M that can be correlated with the locale of the solute. The same thing for the maximum solubility, the same thing for the B. This is to say that you have the three parameters of your model that you correlate to the log of Cal. Do you remember that before I showed you that it's very important, the non-polarity of the hydrotrope? Now I'm showing you that it's very important, the non-polarity of the solute itself. And with this, we could convert this conceptual model into something that is usable by a formulator with curves that these curves now are the correlations of the data and the predictions of new systems. So now we really can have a model to predict the solubility in hydrotrope systems based on a statistical thermodynamic model. And as I told you, 3 regions, and this last region is the last thing that I want to tell you about, because this last region is fantastic. It's so interesting. You have a solvent like this. It's non-very polar solvent, so somewhat polar solvent, but it's a solvent, it's an organic solvent. And then you want to dissolve on this solvent a compound that is poorly soluble in water. And what happens is that when you add water, where the compound is very poorly soluble, you increase the solubility of the compound, the solute on this solvent. And this is so strange that we had to try to understand. And I won't spend much time here, but I can tell you that it's right now under revision in ISCR, that we really think we understood why water can become a glue between a very hydrophobic compound and a organic solvent, leading to this maxima in solubility. And to complete my talk, and that's about 1 hour, it's more than I would like to have talked to you, my final take-home message, that is a citation from a book from UNESCO, a play from UNESCO called Rhinoceros, that it says, I don't just, I will say it in Portuguese. Eu não me limito a constatar fenómeno, eu tenho que o compreender e explicar. And I think this question of explaining something, understanding something is what makes the difference in my work, and that's what has been leading the work, and you can understand this from this presentation, but it's the message that I would like to convey to all of you. Don't just acknowledge a phenomenon. Don't just report that something is happening and that's very good. Try to understand it. Try to understand, go back to the basics, because if you really understand it, you can design new things like we did with the euthetic solvents. You can design new euthetic solvents going far beyond what had been achieved, and that's what we are trying to do also with the hydrotropes right now. Final word of thanks again to the team that has been working with me, in particular to Denise that has been doing all this fantastic work with me. And that's it. Thanks a lot. Open for questions if you are still there.
Thank you, João.
Thank you so much.
Thank you, João. That's why we put octopus at the beginning, because it's amazing number of results and new ideas and new things. So and also is for younger. Think about science is not a question of results of work, but very important is the question that you are asked for yourself, and that's a very good example for that.
It's exactly that. Science is not just about going to the lab and make measurements or getting measurements from literature and correlating them. It's about understanding, and it's about creating knowledge. And that's what makes the difference, and that's how we can make a difference in society, by creating these things that are not there, and not just making correlations or just going to the lab and measure. Yes, please.
Well, question is, sorry, Amara.
Today is our date. Thank you so much, Professor Coutinho, for this enlightening presentation. A really excited bug just told me that between here and our YouTube channel, I got more than 160 times 60 simultaneous viewers. So it's a big wow. Congratulations. We are
Thank you.
now open for questions. If you want to ask one, please enable your microphone or write it out at the chat and we will read it. Of course, on our YouTube viewers can write it out also. Yuri will be handling the questions from now on because I have a class just now. Thank you so much.
Thank you, Yamara.
Hi, Yuri. Can I ask the first question?
Sure, go ahead.
Professor Coutinho, that was a really wonderful presentation. Thank you so much for that. I have it's more like a curiosity because for some applications, you don't want the solvents to absorb water. And I was curious about the comparison between ionic liquids that you made. Have you studied the hygroscopicity? I don't know if this is the correct English word for it.
Yes.
Of these similar systems, comparing this with ionic liquids.
Yes. If you are thinking about comparing this based on choline with ionic liquids, I would say that the euthetic systems based on choline are at least as hygroscope as the ionic liquids. Because choline, I mean, if you go to the lab and you work with choline, you will understand what I mean. It's extremely hygroscope, extremely hygroscope. It's impossible to dry it completely, and it's impossible to work it outside a glow box without having it soaking water from the atmosphere. So it's, if you need a system that cannot have water on, choline-based euthetics are not your thing. This said, some of these ammonium are better because they are less hygroscope. Actually, some of them, depending on the size of the alkyl chain, they are not hygroscopic at all. You can dry and have them dry very easily. I mean, these are not the sort of solvents, neither ionic liquids, nor the euthetic systems that you would like to work dry, because of the viscosity, because of many other things. They are good to work in aqueous solution, and most people will report that they have only 5% or 10% of water, but this is mass percent. So actually, even the industrial applications that you have for ionic liquids and for euthetic systems are aqueous based, because when you have 5% weight percent, you are with more than 50% of water. So in most cases, you have plenty of water in your systems.
Thank you.
Okay, we have a question, a commentary and a question on YouTube from Álvaro Silva Lima. DES are quite biocompatible, but interactions with water and biomolecules can cause problems in the extraction process. The recovery of DES and biomolecules from the extraction medium in integrated process can be another problem. What is the perspective for using DES in the extraction of active biomolecules as enzymes? Can DES still be recommended for these procedures?
If you are talking about large molecules like polysaccharides, like proteins, the separation of these things is not difficult because of the size difference. Any membrane process would be good to separate a protein from an euthetic solvent in aqueous solution or an ionic liquid in aqueous solution. The viscosity would be low enough and the difference in size would be enough for a membrane to separate it. So this is not a problem. The problem is when you work with small size molecules, and that's why for those applications Either you design an application where you will leave your solvent on. This leave-in strategy is a strategy that is being used with deep euthetic solvents when they are applied industrially to extract biocompounds, meaning that at the end the solvent is there as solvent for your extract, and you are commercializing the extract on your solvent, and you have designed your solvent in a way that it can be part of the final formulation of your product, or you go to other things. And that's what I've been doing in this last couple of years, working with other solvents, green solvents like Cyrene, like the glycerol ethers, like, I mean, there is a lot of buzz and fuss about euthetic solvents, but in the end, they are just mixtures. And in many cases, you don't even need the mixture. There are so many other green solvents that are far more interesting there in literature, being presented. Every day there are reports of new green solvents that probably you should be looking into other things. I'm not very fond of euthetic solvents.
Okay, just to add, Álvaro Silva Lima also left a compliment on YouTube. Congratulations for the very nice presentation.
Thank you.
Any more questions?
Jesus.
I think Professor Fred is on mute. We can't hear you, Professor Fred.
I have one. When you talk about hydrotrope, normally you say about aggregation. You talk a lot about aggregation. But sometimes maybe it's a microemulsion, no? It's not only aggregation. So, and you use a very simple model.
Fred, in the limit, some people that are working in this area, they call these surfactant-less emulsions. Depending on the surfactant-less emulsions, because, well, the hydrotrope is not an actual surfactant, right? And yet, what you get at the end, in some cases, is essentially a microemulsion. So you are right about that. You are in the colloidal range, depending on the molecules that you are working on, bridging the gap between the conventional solvation and the emulsions. So you are in this intermediate region here. And in some cases, you are truly already, depending on the concentrations of the things, on the microemulsion side.
Because normally, when you think about aggregation, we think about very few number of molecules, like a pair, three molecules, 4, something like that. But it seems to me that you have kind of microemulsion, and that's why it's a thermodynamic. You can calculate by thermodynamics because you have a stable structure that you can calculate.
Yes, but note that the M's that I showed you, and again, the Seishi model is a statistical thermodynamic model, meaning that when you use good data and you correlate this data, the parameter has a meaning. The systems that we have been studying have aggregation numbers M between 1.5 and 3.5, something like that. So we are really in this range with these systems that I studied that are still not fully microemulsions, and where the colloidal aspect is already important to not consider it fully just a solvation thing, an ordinary solvation thing. But other systems with other hydrotropes and with other solutes do form microemulsions. And thus, this concept of the surfactant-less emulsions that many of the authors that work on this area talk about.
Okay. Can I ask a question?
Several, if you want.
This is Luis from Campinas, João.
Olá, Luís, como estás?
Bem, bem. Thank you very much for a very nice presentation. I really liked the way you used also tools like molecular dynamics and Cosmo to interpret and to get new insights on the systems.
Oh, you have to. Just the data is not enough to give you the answers. Sometimes you can even get an intuition about what's going on, but nowadays, I mean, you can just write a paper saying, I think that this is this and that. No, you have to show it, and you have tools to show it. And molecular dynamics is an excellent tool to show it. The Cosmo, not the Cosmo itself, it's essentially all the ab initio that is behind Cosmo. It's an excellent tool itself. And as I show here, I also like to work with spectroscopy. As I show with NMR, spectroscopy is a very powerful technique. It could be Raman, it could be infrared. I mean, thermodynamicists have to embrace these things and no longer just go to the lab and make macroscopic properties measurements. So, sorry, Luis, I interrupted you. You were about to say something. Go on, go on.
That's beautiful. Actually, it's a minor technical question, and maybe I have lost this on the way in the presentation, but I saw that you use some kind of descriptors to understand from sigma profiles, from causes,
yes,
and what's going on. And my question is, when I saw the pictures, of course, they are pictures, so we only see a specific state. So my question is, when you calculate these descriptors, you run the calculation for the mixture, because I think the charge distribution will be different for molecules.
No, Luis, no, we do not. We do not. We always, the descriptors are based on the description of the pure compound in this infinite permittivity medium that Cosmo uses.
Okay.
I agree with you, and I'm sure that this would explain not only the scattering that we observe in some cases, but also in some cases, and we were discussing this a couple of days ago, probably why some molecules we cannot describe at all.
Yeah.
Because when you embed them in the solvent, the distribution of the charge, the way they interact is completely different. This is probably even true in that case that I show of the thymol menthol. We are still working on that, trying to understand better. We did Raman on that. We are doing more MD calculations. And well, I present you a very simple version of the thing, saying that, well, you see this resonance creates a very big acidity on this proton. And this is true, it happens. The problem is that this resonance is induced by whatever is around it. When you have pure thymol, the acidity is completely different than when you have it with menthol or in different dilutions. And really, for instance, what you can see in the Raman, it's that it goes through a maximum, suggesting that the effect of the second compound, the environment, is very important. Yes, it is very important. But I mean, you have to simplify things to a certain extent, otherwise they will become impossible to work, as you understand. Yeah.
Thank you so much. Congratulations. Beautiful work. Beautiful work. Thank you.
Thanks, Luis.
Okay. Thanks again, Professor João Coutinho, for the presentation. Thanks everyone for the discussion. We're wrapping it.
May I make a last question? It's just because so. I was very curious about this hydrotropes nomenclature, and I just typed here on Google, and I found very few numbers of hits. It's 108,000 compared to, for instance, if you use drug delivery systems, that is a much more complex keyword. It shows 11,400,000 occurrences. And then I found a paper I found a paper on Langmuir that is entitled, "Are Hydrotropes Distinct from Surfactants?" And they kind of conclude that there is little to suggest from this study that hydrotropes differ in association behavior from regular surfactants.
Yeah, indeed. Julian Isto, he reported that almost 20 years ago. What is interesting with this hydrotropy thing is that it's a tool extremely used in the industry. If you go to any company that does formulation, they are using hydrotropes. We are using the concept as a tool for the development of the solvents with much success, and is poorly studied and poorly understood. I think, and we tend to believe nowadays here in my group, that the word hydrotrope stands for not one phenomenon, but a broad range of things that explain the enhanced solubility in water in presence of a third compound. And it's not one phenomenon. And all this work that we are doing, it's based on one concept, this concept that is the basis of this statistical thermodynamic theory of Shimizu. And for instance, Kuntz would disregard the work that we are doing, saying that this is just an aspect of hydrotropy. And I agree with him. This is just an aspect of hydrotropy, because hydrotropy covers many other phenomena. But for this particular phenomena that we are working on with these particular compounds, I mean, I showed you styrene. You don't think that styrene is a surfactant. You look at the styrene molecule again. Do you think styrene is a surfactant? Do you think that it self-aggregates, that it forms micelles? It does not. And yet, it behaves as an hydrotrope. So clearly, there are more to hydrotrope than Isto says and then the Seishi model just alone says. It's a complex thing that is poorly studied, and I think that we are bringing new light into this field. What I would challenge you is to think about your solvents, not just in the conventional way, because there are other ways of solvate a molecule, of dissolving a molecule. And surfactants is an extreme case, a common solvent is another extreme case, and in between there is a range of things that may be happening, and they are poorly understood and they are not explored. And that's what I'm trying to do. And yes, it's true that there are so few people working in hydrotropy nowadays.
Well, thank you for your explanation. It was actually very interesting to me also, because I work with drug delivery systems and trying to solubilize pharmaceutical compounds. I mean, I work with modeling on that, but I have never heard about this term before. And now I'll pay
but in pharmacy, you have most of the works on hydrotropy, they come from pharmacy.
Yeah, that's why I'm so surprised. Maybe yeah. I haven't looked at the right literature. Thank you.
Well, there's one more question in the chat, if you don't mind answering. João Coutinho, can I read it for you?
Yes, please.
So read it for everyone. How does the deep euthetic solvents N and ion influence on the delignification in wood? The lignification with ionic liquids depends on anion size.
That's an excellent question. There are many people that have been doing delignification with ionic liquids, and we know exactly how it works. There are a handful of groups working with delignification with euthetic solvents. And the data that we have so far are not enough to understand completely the mechanism. Those systems that I studied, and there are other authors that have been using a similar approach, they work through hydrotropy. And then it's not a matter of the size globally, but of the, as I show in my presentation, of the apolar region of the hydrotrope that has to have the right size to enhance the solubility of that particular compound. If you have to have a good match between the two. But again, there is only a handful of people that have been doing that. The data is not enough to give you a clear answer. But one thing I may tell you, it's not related just with the size of one of the parts of the euthetic. The acidity is very important as well.
Thank you. Well, would you mind answering a last question from YouTube?
Please, go on.
It's from Ranieri Lucena.
Yes.
He's asking, which DS application will be the first to be industrially implemented?
Oh, there are already a number of them. Go on with your question.
Yeah, I think it's a comment after the question. Despite all their benefits, until now, no industrial application is known, but the use of DS in nanotechnology, biodiesel production, extraction, and metal is currently under research.
He's talking about euthetic systems, right?
Yeah, euthetic solvents.
Okay, okay. If it was about ionic liquids, I would recommend a book by Mark Shiflett that has appeared a couple of months ago on the industrial applications of ionic liquids, where they review 50 different applications of commercial applications of ionic liquids. As euthetic systems, there are applications of euthetic systems. It's younger than the other, but I mean, when you know Andrew Abbott, he didn't create the euthetic systems to be a curiosity. He's a hands-on person. He created his own spin-off, and the reason why he used choline chloride is because he needs for electrochemistry applications, electroplating, dissolving metals, and so on, the high concentrations of chloride. And I mean, there are photos of applications, industrial applications of euthetic systems in electrochemistry, that in process that he developed together with companies, and that's why I always say, ask yourself if you need the chloride, because Andrew Abbott, he needed the chloride. He didn't choose the choline chloride just because. It was important for him, high concentrations of chloride. For most of you, probably they are not. And he also worked with a company, Naturex, in France, that do extractions of natural products to incorporate in cosmetic formulations. And that's the strategy that I told you about of the leave-in, where they developed the euthetic solvents that they use to do the extracts, to prepare the extracts, and then they sell this thing, the solvent, together with the extract. And the formulation is prepared directly with this, you see? So there are industrial applications of this.
Okay, so now it's really time to wrap it up. I have some final announcements to make, but first let us thank again Professor João Coutinho for this great presentation.
It was my pleasure to be here with you.
Thank you, João.
Obrigado, Fred, pelo convite. Um abraço a todos.